Alright, so this is equilibrium number 3 that we're doing here, or equilibrium video number 3. And we're looking at the slide here about Le Chatelier's principle. See if I can get this to behave there. There we go. So we're talking about Le Chatelier's principle. Le Chatelier's principle is something that basically explains how equilibria respond to stresses. And so one of the first learning objectives is to figure out what are the different ways we can stress equilibria, and then to be able to predict what the response is in response to Le Chatelier's principle. I think Le Chatelier's principle applies to a lot of things, and you can think of the situation we're in right now with the COVID-19 social distancing and restrictions that we have, and the fact that our classes had to go online. That stressed our equilibria that we normally live in, and we're going to respond to that in certain ways, and we make changes. It's interesting to think about it that way. All right, anyway, but in chemistry, Le Chatelier's principle is going to be a little bit more concrete, and we can do calculations and things to see what's going on. So what happens? You got a reaction, you got an equilibrium reaction. It's at equilibrium, and at that point, the reaction quotient Q is equal to K. So you disturb it somehow, and that disturbance changes the value of Q, which means that Q is no longer equal to K. Okay. So not equal to K here. And at that point, based on whether Q is greater than K or whether Q is less than K, like we talked about before, we're going to shift to reestablish that equilibrium. Again, generally speaking, since Q is equal to products over reactants, if Q is less than K, that means we're going to shift towards the products. And if Q is greater than K, we're going to shift back towards the reactants. So, what are the stresses? Well, one of them is adding a reactant or product, or removing a reactant or product. Okay, adding one is easy. You just put some more of that stuff in. Removing one might be a little more tricky. You might precipitate something out. You might condense something out. Somehow you're able to remove something if, like, say, if it was a heterogeneous equilibrium and only the products were gaseous and you let some of the gas go, then you could stress it that way. Anyway, though, if you add or remove a reactant or product somehow, that's going to stress the equilibrium, and generally the equilibrium is going to respond to try and relieve that stress. So if I add a reactant, it's going to try to react in such a way that it reduces the amount of that reactant I added. So shifting towards the products. If I add a product, it's going to shift back towards the reactants. If I remove a reactant, it's going to shift towards the reactants and try to replace that reactant I removed. If I remove a product, it's going to shift towards the product and try to replace that. This is important sometimes if you're doing a synthesis in organic later on. When you look at something called the aldol condensation, for example, you'll see that one trick at one point is to precipitate a product out, and that pulls the equilibrium all the way forward so that you're not limited by the ratio of products to reactants. You're able to actually get everything to go all the way to products, so you kind of get around the fact that it's an equilibrium. Again, pure liquids and solids don't factor into K or into Q, so that doesn't have any effect whatsoever. Again, as long as some of it's present, it's still in play. So here's a picture of a soft drink bottle where actually this is, I think, a soft drink that's put in an Erlenmeyer flask maybe, and you pop the top there, and what's happened is the release in pressure has caused more CO2 to go into the gas phase, and you see the bubbles forming like that when that happens. Temperature changes are another way that happens. If we look at an equilibrium, you basically have two possibilities. So if my equilibrium is reactants going to products, just generally, the two possibilities are that the reactant goes to the products plus heat, or that the reactant absorbs heat to go to the products. This is called an exothermic reaction, and you learned before in Chem 131 that means delta H is less than 0, it's negative, and here this is an endothermic reaction where delta H is greater than 0. The key thing, though, is to think about where the heat is. Is it a reactant or a product? Here, heat's a product. And so if I increase temperature, in this case 1 here, if I increase temperature, I'm adding heat in. That's like adding a product. It's going to shift it back towards the reactants. In reaction 2 here, the equilibrium 2, if I increase heat, it's a reactant, so that's going to shift the reactants towards the products. If I cool the reaction down, it's going to have the opposite effect. And again, this is one of those things that temperature, of course, is temperature K depends on the temperature, the equilibrium constant. Basically, the only thing that will change it is the temperature. So in this case, you are actually changing the temperature when you stress it. So it isn't so much that Q changes there, it's K changes and then Q has to reach it again. So here's the summary of those things I just mentioned on the previous slide. All right, so that gets us to the idea of doing equilibrium calculations. And this is really, for me, this is where I finally figured out that algebra was something that was worth knowing, because I could do these kind of calculations, which may seem strange to you, but I'm a strange person. So, but what we're going to do is we're going to take our equilibrium system. We're going to identify the kind of changes that could happen. We're going to come up with an expression using the equilibrium expression, or the law of mass action. We're going to come up with an algebraic expression that lets us calculate things like the processes. In terms of these last 2 learning objectives, that's going to be in the next unit. So don't worry about those. We'll chop those off of this unit. All right, so the kind of equilibrium calculations you might do, and again, it's always a good idea to think about what are the types of problems I might get thrown at. You might calculate an equilibrium constant given some data. You might have a situation where you have one of the equilibrium concentrations or partial pressures missing, but you have the rest of them and you have the equilibrium constant, and you have to figure out the missing one. And then the most common and hardest kind of problem is where you have to basically, given some initial concentrations or partial pressures, you have to get the equilibrium concentrations. Principles are all similar, okay? And on slide 40 here, we see this thing here, which is called an ICE chart or an ICE diagram. I stands for initial concentration, C stands for change, E stands for equilibrium, and it's absolutely crucial to use ICE charts. Frequently when I'm doing partial credit on a free response question, I'm going to look at the ICE chart as, you know, if you draw the ICE chart and you get certain things in it right, that's going to get you partial credit. So this is a problem here where you're looking at an equilibrium up here. This I2 plus I minus yields I3 minus. That's called the triiodide ion, DE ion. And then of course this is iodide. And this is iodine. And again, chemistry is very picky about nomenclature, but that's that. And this is a situation where you were given the initial concentrations, that iodine and iodide were both 1 times 10 to the negative 3 molar, and either it said or it implied that there was no triiodide ion. And so usually I have students over here calculate Q. Well, Q for this reaction, if I write K for this reaction up here, that's going to be the triiodide concentration divided by the I2 concentration times the I minus concentration. Everything I think is AQ in this, right? It didn't label it here on this, but they're all AQ. So Q here for this, if I take those values, I'm going to have 0, the triiodide value on the top, times 1e negative 3, that's 1 times 10 to the negative 3 for the I2, times 1 times e to the -3 on the bottom there. And again, we don't worry too much about units in these. That comes out to 0. I don't have to do the math there. Whatever the bottom of that comes out to doesn't matter because the top's 0. So that's 0. Now, I don't know what k is. It's not given in this thing, but obviously 0's got to be less than k. And so that tells me if Q is less than K, I've got to go towards the reactants. That's how I get that positive sign there. To the products, and I've got to remove reactants to do that. So I have negative, negative, and plus. That comes from Q. And then the X there is, we write X and we normally multiply by the coefficient. And in this case, all of these are 1. In this case, so minus 1x plus x is our change line. Then what you do to get the E line, the equilibrium concentration line, is you sum I plus C. So in the iodide case, the iodine case, I2, we have 1.00 times 10 to the -3 plus negative x. So our equilibrium concentration line is 1.00 times 10 to the -3 minus x. Okay, so that's our value. So if we plug this in, we take these values and plug in the k expression, we get that k is equal to x over 1.000 times 10 to the -3 minus x, and that quantity squared. Now what I'm doing there is I'm saying that this is I3 minus, which is our x, over I2 times I minus, and I2 and I minus are exactly the same value. So when we multiply them together, we can say that's just squared, like that. And you may recognize that this is a quadratic. And a lot of times we might have to solve that using the quadratic equation. We may have tricks that make it easier for us. We can't really do anything with this because we don't know what k is, but usually we'll know, on this kind of problem, we would know what the value of k is. But that's sort of how you work on an ice chart there. So here is a situation where the changes have been identified. So we could calculate what k was based on this. So again, k is going to be I3 minus over I2 concentration times I minus concentration. So we're going to have 3.39 times 10 to the -4th on the top. And then on the bottom, we're going to have 6.61 times 10 to the -4th times 6.61 times 10 to the -4th. And, all right, where's my calculator? If I plug that into my calculator, and again, this is a great opportunity for you to check that you can do this. Remember that if you're plugging in a TI, you want to use that second comma for the EE function. So 3.39 second comma -4 would be the way you do that. And x1 negative squared. All right, so when I did this, I came out with a value of 776 basically. And k values, we again, usually we don't worry too much about sig figs here. These tend to be good only to about plus or minus 5%. A lot of uncertainty in them, but that's what we get right there, is 776 in this case for that value. Here's another ice chart. Now we have an equilibrium here of PCl5 and PCl3 and chlorine gas. Again, all these things are in the gas phase. So all of them are being looked at as concentrations. We can still talk about gases in concentration units if we want to. And we start off with only PCl5, and Q, of course, is 0 times 0 over 1 because K here is PCl3 concentration times Cl2 concentration divided by the concentration of PCl5.